Okay, good afternoon. Let's start lecture. Okay, so we'll continue on the topic of the double integral. Okay, if you recall from our last lecture, we formulated the definition of a double integral, and we gave an example of how to compute double integral in Cartesian coordinates. And we started an example of calculating double integral in Cartesian coordinate using x and y. It turned out to be very complicated. So we said we can have another option. Basically, maybe we can evaluate the double integral using a different set of coordinates. What we call is basically polar coordinates. So polar coordinates, essentially, it's in the same kind of a plane as xy, basically a Cartesian coordinate here. But this time, you're using, instead of using xy, you use r theta to represent the location of a point P. And the relationship between r theta and x and y is pretty simple. Just x equal to r cos theta and y equal to r sine theta. Okay? So basically, okay, this is the connection between polar coordinates and Cartesian coordinates. Polar coordinates are very useful coordinates because sometimes when you wanted to plot something, it's actually better to plot using polar coordinates. So this is one example here. This is called a cardioid kind of a curve. So the formula is this: r equal to 1.5 minus 1.5 sine theta. So you can plot using MATLAB Maple very easily. If you change the theta to some other angles, so like a 2 theta, 3 theta, or 5 theta, you have basically like a flower. Three petals and then 4 or 5. So they will basically expand the number here. Okay. Now, however, if the same curve, and if you wanted to express the same curve using Cartesian coordinates, I don't have it here. It's much long expression than this short one here. Okay? Yeah. So basically, it's a different perspective. Looking at the things will give you an advantage if look at it differently. Okay. So now the question is, how do we evaluate double integral in polar coordinates? Okay, yeah. So essentially, what we want is, here is a double integral, okay? But we want to, change this one, to a different double, not same, still the integration with respect to f, okay? But the whole thing is, so the x is going to be changed to r cos theta, and y is going to be changed to r sine theta. The dA at here, this is a dx dy at here, okay? Dx dy. So what we're going to do is, we will have the same thing. We're going to integrate now with respect to r and theta, but the only problem is, what will be this one here, okay? This is what we call basically a so-called scaling factor, okay? So basically, you see, dx dy represent what? This is basically representing as an area element in this xy plane, right? In xy plane, okay? Or in the xy variable. So now we have a similar stuff. So this portion out here, okay? Not this portion. This portion, okay? This portion should be an area element. Okay. Is that raining? In r theta. Okay, so there's a scaling here. So this area and that area, there's a scaling here. But supposed to be, they should be the same kind of area elements. Okay, yeah. Okay, so let's figure out this question mark here. Okay, Now, if you remember, in xy plane, it's pretty easy. How do I get the area element? Basically, you take a delta x, delta y, multiply them together. It's rectangular, and that's the area element. So now in polar coordinates, it's r and theta. So what do we do is, okay, so this is the second question here. So let's relate this dA to dr and the d theta. So here's what we do. How do we do? How we relate the these two parties at here? Okay, so dr and theta. So theta is basically it's a changing around this vertical z-axis. So it's a rotation, right? So this is basically there's a theta change, and r is a what a change. R is a change in terms of this. Was that right? Yeah. Just like x, x-axis change, delta x. Y, so that's the change. So let's draw some reading lines at here. Okay, so I'm going to draw some reading lines like this. Okay, at the same time, okay, I'm going to draw some clusters of curves like that. Okay, so now you see, if I wanted to use a certain so-called area element, what I can do is I can pick an area element like this way, okay, like this. So there is a change, basically there's a change in the r direction, and there's a change in the theta direction. So delta r, delta theta, basically that will form this small area element in here. So let's explode this one a little bit bigger here, okay? So let's explode it. Okay? Yeah, that would be the best background for the video. So we'll explode this one here. Remember what I said? We have, this is R, so this is basically, let's use a circle here. This is R, and there is a change, okay, in the R direction. So this is a delta R, okay? So there's R direction here. And this is a theta, and then there is a small change in the positive theta direction, so this is a delta theta. Okay? Yeah. Then the small area element is sandwiched between these four curves over here. Okay? So the question is, what is this area, okay, for these small elements at here? So if it is everything small, and we can consider this as a rectangle again. Okay, so we can still consider it as a rectangle. And what are the four sides of rectangle? Here, 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 right? Then what are the lengths of the rectangle then? So this side, the length is actually what? The dr or delta r, right? And this side here, consider this side and this side is the same thing. So basically, what would be the length, approximate the length for these two sides? It's going to be what? R times this angle. Was that right? Yeah, so that's basically the arc length. This arc length right here, okay, is R times delta theta. So then the area element, so small area is basically the delta A is going to be approximately equal to R delta theta and delta R. So one side times the other as a rectangle, a rectangular area. Is that right? Yeah. So imagine then if you have as many as possible as n goes to infinite, so this delta becomes basically the symbol D, right? So in other words, dA is equal to R, dr, and d theta. Okay? Yeah. Is that a question or just okay? So there we go, right? This is what we're looking for. What's the connection between dA and the dr, d theta? So the small area element in the polar coordinate is r dr d theta. So back to this general formula here. So what should I put it here to replace the question mark then? Exactly, just the r at here. Okay, yeah. So there we go. You basically transformed the original double integral in xy plane, in xy variable, into a new double integral in r and theta variable. So technically, for this r, okay, we should call that probably different r here, maybe r prime. However, this is a special case. When you have an xy plane and polar, particularly if a circle, anything, that area R, okay, is still there. So we can still use R. But later, I'm going to show you a different case, basically in more generic transformation. So in other words, you may not evaluate this in terms of x, y. Maybe you're not going to transform that using polar. Maybe you're going to transform this x and y into another set of variable, u and v. Okay? So basically, not necessarily we always have to use polar or x and y. We can actually use another totally different variables, u and v, or w and z, who knows, right? But we're going to talk about that later. So, but for now, it's a transformation from x and y to polar coordinates r and theta. Okay, that's it. So this is basically the formula, okay, for evaluation. Okay, so of course, the next job we need to do is, in order to evaluate this one here, we need to figure out what? We need to figure out the limits for r and theta. Okay, so if we can figure out the limits for r and theta, then we can compute this double integral. Okay, so let me give you a more generic summaries here in terms of finding the limits. Okay, and then we'll look at examples. So finding limits for r and theta. So here I'll use this sample region, okay, for illustration. Okay, so suppose that I have a region R like this. Okay, so region R is bounded by, on the most outside, it's a part of the circle. Okay, it's part of the circle. X squared plus y squared equal to 4. And then the bottom here, this is of course this is a straight line here. Okay, that's y equal to root 2, for example. Okay, yeah. And then there is this y-axis. So together you have this region R. Okay. So this is the region R, and we're supposed to integrate a certain kind of a function, okay, over this region R. Normally, when you see a boundary with a certain kind of a circular kind of a boundary there, okay, it's a common sense usually polar coordinates will work probably easier than Cartesian coordinates. Okay, yeah. So to figure out these limits, here's the steps you need to do here. Okay, so step number 1. Okay, so what you do is basically you draw a reading line. Okay, from origin. Okay, draw an origin line from origin across the region R. Okay, the region R. So here's what I'm going to draw here. So let's say draw. Use red color. Let's draw a reading line here. So starting from origin, draw one. Where did it go? Yeah. Draw a reading lines, okay, across this, okay, region R. Okay. Like that. Okay. So once you draw this one out, you will see that this reading line will come into contact with the region R with the first contact over here, and with the second contact at here. And what we call this is basically the entry point, and this is basically the exit point, right? Yeah. So Imagine there is a guy walking. So that's the first contact, that's the second contact. Why? First of all, why am I drawing a reading line out of origin like this? Because how is the R defined for polar coordinates? R is always defined as what? From the origin to certain point, right? So in this particular case, from here to the first contact, so this first, from the origin to the first contact, that distance represent is the R what? R minimum, the minimum limits for R. Okay, so basically R mean is the distance, okay, from origin to first contact. Okay, so in this particular case, this portion is R mean. Okay, it's R mean. Okay. So similarly, R max, okay, is the distance from origin to second contact. Okay, so but basically it's the distance from the origin to here. Okay, to here. So if I use a bigger here, so this is R max. Is that good? Yeah. So once you figure out this R mean and R max, okay, the next is of theta, mean theta. But let's see in this particular case, what is the value for R mean and what is the value for R max? Let's do the easy one. Which one is easy actually? R mean or R max? R max. So R max must be always equal to. This is the radius, right? Because the second contact point is where? It's on the circle. So this is from here to here. That's the radius of the circle, which is 2. Yeah. So R max basically is 2. Okay. So then what is R mean then? Right? Now we know the definition of R mean now is from here to the first contact. So this side here is R mean. So often in time, in this kind of particular case, you're going to have to use a certain geometric relationship to get the expression for R mean. So what we resort to here, we can resort to the geometry here. So this location is actually what? This is square root of 2 because that's y equal to, right? And this is a 2 at here. Okay. What else? Now, so before we do that, let's put down another information. So what's the definition of theta? Definition of theta is always the angle starting from x-axis. Okay, theta is always starts from x-axis up to this vector here. Okay, up to this, basically up to this reading line here. Okay, so theta, remember theta always starts from x-axis. And also theta is greater than 0 if you're going which direction? Counterclockwise direction. Okay? So it's basically convention, counterclockwise direction. So then in this particular case, where's the theta? So theta is from here to where? To here. That's theta, right? That's theta. Sorry, the drawing is a bit of a mess here. Okay? So that's theta here. So now maybe I'm going to draw that, I'm going to explode that a bit of here. Remember what I said? I'm looking at this triangle, okay? I'm looking at this triangle here. So this triangle. So this triangle, and for this side of the triangle here is R mean, which is what we're looking for. And bottom here, this is a theta. And what's the length of this side? Root 2. Okay, so now looking at this one here, see if you can find a connection between R mean and theta. If this is theta, where else is theta? Right? Okay? So what would be the relationship now? So how do I relate this theta root 2 to the R mean? sine theta equal to root 2 over what? R mean. Was that right? So which means R mean equal to root 2 over sine theta. Okay? Yeah. Is that clear? Yeah. And that's root 2 sine theta is cosecant theta, right? The second is cosecant. Yeah, that's right. Okay? So that's it. That's basically R mean. And of course, you probably wonder, what happened? Why R mean is not a constant? Well, of course it's not, because why? Because if you're going to rotate this, if you're going to draw the reading lines across at a different location, guess what? The R mean changes, right? The R mean changes. So that's why this is not a constant. Okay? Yeah. So the next step is so the next step is you do this. Basically, the next step you sweep this reading line. Okay, sweep the line you just draw here across this region R. Okay, cross the region R, and you find the bounding location when you're sweeping. So in this particular case, what are the two bounding locations? One is here, right? And the other is here. So there will be two theta values associated with the two bounding locations. One is at here, and the other is at here. That make sense? So the theta value corresponding to this one is theta minimum. And the theta value corresponding to this one is theta maximum. Okay? Yeah, so this is the next step you do. Okay. So step number, well, doesn't matter. Step number 2, okay, sweep this reading line L, okay, across region R. Okay. Find the bounding angles, okay, theta. Okay, so in this particular case, I'll draw it here again. Okay, so you have one is over here, and one is over here. So that's the two bounding location. And this is root 2, and this is x squared plus y squared equal to 4. Okay? Yeah. So for the first bounding reading line, for this first one here, we call that the corresponding angle, the theta mean. And this one here, right, is the theta max. Okay, that's the limits for theta mean and theta max. Okay, that makes sense? Yeah. Okay, so let's take a look at this region here. What's the value of theta mean and theta max? Theta max, I guess, is pretty easy. Remember how theta is defined. Theta is the angle defined from x-axis to where? Basically to where the reading line is. In this case, is y. So counterclockwise is positive angle. So you go this way counterclockwise. So that's basically what? Pi over 2. Okay? And theta mean. Well, I guess theta mean depends on this point, right? If you can figure out the location of this point, then you will be able to figure out this theta mean at here. Okay? Yeah. So essentially, what's the location of this intersection point between this straight line and this circle here? Okay. So what would be the location of the line? What would the coordinates? What's the coordinates here? Root 2, yes. So if the root 2, so that means the theta mean must be pi over 4. Okay. Is that clear? No? Well, First of all, what will be the y-coordinate for point A? That's easy, right? The y-coordinate of point A is, this is constant. It's root 2. Okay, right? For A here, it's a root 2 as a y-coordinate, and point A is on the point A is on the circle. So you plug it into the circle. So root 2 square equal to 4, and you end up with x equal to root 2. Okay, so that's how you get this. So basically that's it. So in the end, you lay down the double integral based on the limits that you found. The first, basically f function, any f function, the x will be replaced with r cos theta, y will be replaced with r sine theta, then dr, r dr, and d theta. Don't forget this r. The limit for the r is, as we figured out, is what? It's this. R mean is root 2 over sine, and top is 2, and theta is from pi over 4 to pi over 2. Okay, so that's the layout using this polar coordinates. Yeah.
Where did theta come from?
Where did theta from?
Theta minimum.
Also, where is theta minimum from?
Yeah.
Theta minimum is the theta angle corresponding to this boundary here. Right? See, this is the basically the two lines bounds this region R. Right? So this line here bounds the region R. Is that clear? Right? So then the corresponding theta angle for this line is the theta mean. And this line here passing through this point A, basically. So apparently point A has a coordinate root 2. So that's why this is what? Pi over 4. Yeah? Remember the idea of sweeping. What are we doing? You're integrating over region R. When you're integrating over region R using xy coordinates, remember the sentence I said, you're sweeping through region R without redundancy. So how did you sweep? You basically did a either x direction or y direction cut. Then you sweep through in the other direction, right? So this way you basically touch every location. So you see same thing here. You watch the operation. What's the first operation? The first operation, you draw a line here. Basically you end up with this portion, right? You end up with this portion. And the next operation is what you did is we're sweeping these reading lines across the region R. So imagine that. So this line here will basically sweep through this region R here, right? So that way you're integrating over every corner of the region R. Okay, is that good? Yeah. So that's basically the idea of the polar coordinates here. Okay? So let's try that difficult question that we couldn't solve using Cartesian coordinates, and let's see if we can solve that using polar coordinates. Okay, so here is region R in the previous lecture. X squared plus y squared equal to 1. That's a unit, basically unit circle, only quarter of that. What we want to integrate is y squared, okay, over this region R. Okay. So it turned out to be pretty complicated integral if we use Cartesian. But now let's try polar. Okay, so polar coordinates. Okay, so let's put down the easy part. Y squared. So what do we do with the y again? The y will be changed to r sine theta. Okay, so y will be changed to r sine theta. So in this case, it's y squared, so r sine theta squared. And dA is going to be changed to r, dr, and d theta. Okay. So then the next step is let's figure out the limits for r and the limits for theta. So according to the procedure, what do? Starting from origin, draw a reading line across this region R. The first contact between this reading line and the region R is R mean. So where is the first contact point? 0. Second is here, so 1. Right? Pretty good. Second, and then you sweep through this reading line across this region R. Find the bonds and find the bounding angles. So apparently, the bounding lines, one is here and one is here. And for the first one, it's theta equal to 0. Second one, pi over 2. Yeah, we'll see. Where's this from? Y square? Sorry, you know what? Oh, why is it y square here? Oh, well, you could put anything here. Just pick y square. Yeah. What's wrong with y square? Oh, you like x squared? You can do like x squared. Yeah. So.
What does that look like graphically?
Y square?
Yeah.
So basically, this is f. Well, your double integral is this, right? This is double integral. F of xy. Z equal to f of xy essentially is a surface, right? So if this is z equal to y squared, what does it look like? If you draw the z equal to y squared, if you draw the z equal to y squared in the zy plane, what does it look like? It's a parabola, right? It's basically a parabola like this, right? But this is a 3D case. So what do you do with this guy? You basically extend this parabola to the positive and the negative of axis. Guess what you're gonna get? You're gonna get basically spell drawing. So basically you're gonna get like this, right? You're gonna like this. That make sense? Yeah? Okay. Is that clear? You got 100%. You asked me this question. So, anyway, R mean, R max is 0 to pi over 2. Okay? Okay. So this is a pretty simple, I think, in terms of the integral now. Let's see, what do we do from here? Inside here, this is r squared times r is r cubed. And there's the sine theta, of course. So when you integrate it with respect to r, you treat the theta as a constant. Oh, sine squared, yes. R cubed, that's 1/4 r to the power 4, 0 to 1, and d theta. And then sine theta here. Okay? Yeah. Sine theta squared here. So so this one here, sine theta squared is 1/4, right? D theta. Okay, that's it, right? That's this as far as you go it here. So how do we do with sine theta? Trigonometry. I think sine theta squared, if I remember correctly, +1. I don't remember now. It's something like that. Okay?
1 minus.
Oh, 1 minus, yes. Good. Excellent. Yeah. Is that okay? Right? So then you plug it here. So 1 minus cosine 2 theta over 2 times 1/4. I'm going to put a 1/4 outside here. Okay, so then everybody should know how to integrate this one now, right? For cosine 2 theta, you can use a substitution that u equal to 2 theta, and then but usually that's pretty simple. So 1/4 times that may be 1 over 8. So that's pi over 2 for the first one, okay, and minus 1 over 8 for the second integral, cosine 2 theta. For cosine 2 theta, okay, maybe I'll just carry this out here, okay, d theta. Okay, so this is how I use substitution rule, maybe a little bit different from most of you guys here. So what I normally do is this, so watch carefully here, okay? So I'm changing the theta to 2 theta, okay? I'm going to change the theta to 2 theta because I got a 2 at here, and d2 theta equal to what? To d2 d theta, okay? 2 d theta. But I'm adding a 2 here. I can't add a 2 because there's no 2, so I divided by a 2 here to get rid of this 2, okay? But now I got cosine 2 theta and d 2 theta, so same variable, 2 theta, 2 theta. So that basically means this integration here is what? Sine 2 theta, okay? Sine 2 theta. And then goes from 0 to pi over 2. Okay? So sine pi is 0, sine 0 is 0. Actually, the second term is all 0, right? So this is 0 here. So you end up with pi over 16. That make sense? Yeah. Yeah, I know my way normally will throw people off for this substitution here. So what you can do is let u equal to 2 theta. Okay, just keep going. Yeah, it's pretty simple, all right? Any questions? It's all good? Yeah. So let's take a look at the next example, okay? And that should be okay for the polar. Okay, so I have a region R. Okay, inner one is this, and outside one is this. So two half circles. Okay, two half circles, and give us a half donut. Okay, and this is R here. And let's integrate this one. So y dA. So the integrand is y. Okay. And apparently, you will have a difficult time if you integrate this using Cartesian coordinates. So let's convert that into polar. Okay, so same thing. Put down the double integral here, and y is changed to r sine theta, and dA is r dr d theta. Okay, that's as much as you can do very easily. Then the next step, you draw from origin, okay, a reading line across this region R. Then the first contact between this reading line give you the R mean. Second contact in the reading line and the outside give you the R max. So apparently R mean equal to A, and R max is B. Does that make sense? Yeah. Then you sweep this reading line across this region R. So basically it doesn't matter how you sweep, but you need to figure out the two bonding locations, right? So one is here, one is here. And the first one corresponds to the theta mean, which is 0. And the second one is this location, and that angle goes from here to here, counterclockwise, which will be pi. Okay? Sorry? A to B, right? Oh, B squared, sorry. Yeah. Good point, yeah. Yeah, actually that is a common mistake often seen in exam. You know, when I put x squared plus y squared equal 25, so the readings, right? And often there are some mistakes sometimes with that. So that's it. That's basically the layout of this, and then you can carry out this integral. That's very straightforward. Okay, so that should give you. Okay, that should give you this. And if you're interested, if you have some time to kill, try the Cartesian coordinates. Okay, and you can guarantee you won't be able to finish in half an hour. So, but this one, right? 1 minute. Okay, so any questions on the polar coordinates? So good? Okay. So then, before we move on, I'll teach you a very interesting, but generally you don't see the significance yet, okay, at this stage. Basically, it's in a more generic sense of so-called change of variable. Okay, change of variables. And it will introduce this concept called Jacobian. Yeah. Now, yeah, this Jacobian, not exactly the same as Jacobian you learn in numerical analysis. Well, they're pretty much the same thing, but okay. Yeah. Well, I guess that shows how important this Jacobian is, though. Huh? You'll see it quite a bit in many other applications. Okay, so here is the idea here. Here's the double integral. Okay, here's the double integral. And now, what we know is we know that x is a function of u v, and y is also a function of u and v. Okay, somehow you know this. Okay, just pretend you know that. And actually, it's a skill that you need to figure out the proper relationship between another set of variable u and v. So the objective is, I don't want to integrate with respect to x, y anymore. I think I'm going to integrate using this new variable, new set of variable, u and v. So essentially, the point is, we're trying to transform from this double integral to a new double integral. The transformation involving two parts. One part is this r will be transformed into another kind of a shape of a region, r prime. At the same time, of course, the x will be replaced with this function of uv, and the y will be replaced with this function of uv, and this dx dy will be replaced with du dv. But there should be a scaling factor here, okay, to match this transformation. Okay, so the whole point is, what is this question mark at here? So just like the polar, right? Just the polar. But this time, this is a more generic question, right? Yeah. So what we do is, let's define, so we try to find the question mark. So let's define a vector function . So basically, I'm defining using this x of uv and this y uv to form a vector function. Okay. Then, as you learned in numerical analysis, I believe, so what is the Jacobian now? The Jacobian matrix J, given this vector here, it's basically what? Partial x over partial u, partial x over partial v, and partial y over u, and partial y over v. Does that ring a bell? No? Really? I thought you learned this. Not yet? Oh, but anyway. Yeah, that's okay. Just accept this. This is a definition. They're actually. You ask me where is this from? Who knows? This basically a mathematician came up with this matrix, and then it turned out such a useful matrix. Okay. Yeah. So you have basically you have a vector. This is a function. It's a vector function containing two functions that are here. And then when you take a partial derivative, right, of this function yf with respect to xy, you get this. Okay? Yeah. And that's basically a matrix. Okay, it's a matrix of function u and v. And then from here, we're going to calculate the determinant of this Jacobian matrix. Okay? So Jacobian determinant. And we use this absolute value g here to represent the determinant. So determinant, this is a 2 by 2 matrix, right? Okay, 2 by 2 matrix. Okay, so 2 by 2, what's the determinant? This is basically, you can calculate this, multiply this, minus this, multiply by this, right? Quite easy. Okay. So sometimes you'll see in the literature they represent this matrix, this determinant using this symbol. Okay, using this. Okay. Yeah. So if you don't like this one here, just forget about it. So, but the point is we can get the so-called Jacobian determinant of this one. Okay, based on the Jacobian matrix. And what's beautiful is, it's the next, basically the conclusion. We have this so-called change of variable theorem. Okay, change of variable theorem. So the change of variable theorem is, remember what we want. We want, okay, this double integral to convert it into another integrate with respect to u and v now. Okay, it's the question mark we're trying to figure it out. Du dv. The question mark at here, or this scaling here, it's basically the absolute value of the determinant of the Jacobian matrix. Okay, so it turned out that this scaling factor, it's basically the absolute value of this Jacobian determinant. Okay, and that is the scaling factor. And this is a generic a theorem. Okay, not just for polar. So polar, I'll show you how the polar is derived based on this change of variable theorem. Is that good? Right? It's not bad actually. So the only new thing here is probably this guy here, right? Yeah. Okay, so let's verify this change of variable theorem. Now, if you're interested in terms of proof of this, I do have some literature I can show you. There is actually a generic proof of this theorem, but it's beyond this class here. Okay. So let's take an example. For polar, if I'm talking a polar here. And what is the relationship for polar is what? X equal to r cos theta, and y equal to r sine theta. So if you do a little one-to-one mapping here, so the u at here is r, and theta at here is the v, right? That's the mapping. Okay. So let's see what is this guy here. If I use a polar, we know what this is. This one's supposed to be what? Supposed to be r, right? Supposed to be r. So let's verify that. Okay. So how do I verify? I need to calculate this matrix and then determine the matrix here. All right? Yeah. So absolute value for that. Okay. Dx partial x over partial u. So in this case, it's actually partial x over partial. What should that be? R. And then partial x over partial theta. Partial y over partial r, partial y over partial theta. Okay? Yeah. And that's pretty simple partial derivative. Partial x over partial r is cos theta. Partial x over partial theta, yeah, negative r sine theta. Partial y over r, sine theta. Partial y over theta, r cos theta. Okay, so that's the determinant, right? That's the determinant. And then calculate the determinant here. That's the matrix. Calculate the determinant. So cos theta times r cos theta minus this times this. Guess what we get? Did you get this, right? Yeah. And what do we do next? This is equal to r. Yeah, it's equal to r. Well, so according to the theorem, what do we need? We need absolute value of r here, right? Absolute value of r. But remember how the r is defined. R is defined as the distance from where? From origin to where it is, right? So the r value is actually naturally positive. Okay, so I basically prove this change of variable for polar coordinates. Okay, yeah. So I'll give you an example here, okay, just to reinforce this Jacobian. Because why this is important, let me tell you. This basically represents a transformation. Here is an example from x, y to u and v. It's a 2-dimension. You actually can extend that to n dimension, basically. Okay? In probability and statistics, in robotics, in some image and analysis or processing, and there are many places this Jacobian is being used like this, right? It's basically provide you with a different perspective of treating things, okay? And it connects the different perspective, right? That's the beauty. Okay, so let's take a look at an example. We want to integrate this double integral, and the r is defined by this. Okay, and the r is defined by this. So first of all, you gotta basically, if there's no sketch at here, you essentially you gotta visualize what does the r look like, right? Yeah. So what does the r look like actually? So what does this mean? If I get rid of the equal sign, get rid of the unequal sign here, 2x minus y equal to 3. That's what? That's a straight line, right? And this one equal to 1. That's another straight line, basically, right? So essentially, here there are 2 straight lines, and you're looking for is the region between the 2 straight lines. And here another 2 straight lines, and then you're looking for the region between the 2. So altogether, the r is bounded by 4 lines, essentially. Okay? Yeah. So I draw this one here and see here. So I draw it out, and that's what this looks like. Okay? Yeah. So this is basically a parallelogram. Okay? Yeah. So this is a parallelogram here. Now, if you insist to integrate over this region R using XY coordinates, okay? If you insist on doing this, and let's see, what shall we do? I'm moving here. Anyway, okay. So, as we learned, when we integrate double integral using the XY coordinates, so what's the steps we follow? Let's say first step is to determine the order of integration, right? So let's say if you decided to integrate using dy first, for example, okay? dy. So what do? You draw a line in the positive y-axis across this region R. Is that right? Yeah. So if I do this, I'm going to draw it like this, right? Is that okay? Yeah. So first contact, second contact, y mean and y max. That make sense? Yeah. But for this particular one here, where's this first contact? For the first contact, which this is actually what? Y equal to -2 minus x, right? Minus x. And where's this second contact here? This is y equal to 2x minus 1. Do you remember that, right? Now the problem is, I draw the line here. What if I draw this line over here, right? And now what's the y mean and what's the y max? This is y mean and this location is y max. So this y mean is what? Y equal to this. And this one here is y equal to this. You see, right? This y mean is different from this. This y max is different from this. So what do you need to do is actually is the next topic I'm going to touch on here. So when you have this kind of region, you cannot solve this double integral in one shot anymore. You have to separate this region R into two regions. So for this particular case, I didn't calculate this coordinates, okay? They might be just on the top of each other. Let's assume they're on top, but that's okay. There may not be, who knows, right? But you're going to separate this one in this case. Let's, for example, you separate that into two regions, okay? Then you're going to integrate basically R like this. So R1 plus R2, okay? Just like the single variable integration, you can do a so-called piecewise integral, right? So you basically you do this piecewise and you add them together, okay? So that's how you can get this double integral here. So we'll look at this. We'll look at an example of this piecewise integration, okay? But for the time being, you probably can see now, well, at least you can have to calculate two double integrals, right? And that's probably a lot of computations. So let's try this change of variable, okay? Let's try to change a variable here, and then we'll see how easy it becomes, okay? So change of variable essentially is what makes it simple. You want the integral, basically you want this the region R to be simple. So at here, what I'm going to do is I'm going to define this 2x minus y as u, and I'm going to define this x plus y as v. Okay, so let's do this. So I'm going to let u equal to 2x minus y, and v equal to x plus y. Okay, so let's see. Let's see if this is going to give us any shortcut. So u equal to this, and v equal to that. And what does that give us in terms for the x in terms of u and v? So you can very easily solve. So you have u and v, solve for x and y in terms of u and v. Very simple. 2x minus y, x plus y. So this plus this give you 3x. So u plus, so that 1/3 u plus v for the x. And y, and you can solve that as 1/3, okay, negative u plus 2v. Okay, yeah. Okay, is that good? All right, that's a very simple linear solving system equation. So then, remember the question. The question is to convert the original double integral, okay, into a new double integral, okay? So the 3x is replaced by the x function. dx dy is going to be replaced by dv du, and the scaling factor at here is going to be what? That absolute value of the determinant of the Jacobian matrix. So what is the Jacobian matrix here? So this is x function. This is x of uv. And this is y of uv. So the determinant of J is basically partial x over partial u, partial x over partial v, partial y over u, partial y over v. Okay? Yeah. A simple partial derivative, right? And the first one here is 1/3, 1/3, and here negative 1/3, here is 2/3, right? And what's the determinant? 1/3 times this is 2/9. Minus, so it becomes plus 1/9. So 3/9, 1/3. So this guy here is basically 1/3, right? 1/3. So then the double integral here, 3 times this is 1, so 1/3. So there's another 1/3 here. So u plus v and du and dv. Okay. What is the limits for the u? What's the limit for the v? You see, when you define this u as 2x minus y and v as x plus y, so you naturally, basically, this is the u here, this is the v here. What's the range of u? It's 1, 2, 3. What's the range of v? It's this. So imagine yourself, there is basically a u and a v, u and a v plane. And what does this new region R prime look like now? U is between 1 and 3. V is between -2 and 0. So it's actually what? U is between 1 and 3, and V is between -2 and 3. So what does it look like? It's this, right? It's this. That's a rectangle, right? It's a rectangle. So it's a rectangle, and what will be if I do the integral here? How do I find the integrals? The u basically is between 1 and 3. V is between -2 to 0. Okay? So you look at this one here. That's very, very simple double integral, right? And that's much simpler than the previous one there. Okay? Yeah. So of course, this needs a little bit of twist of mind to apply the change of variable. Okay? So if you don't like this, you can still work on the previous one. You'll be okay. Okay? Yeah. Yeah. If you like a little challenge of this, you can apply this. Okay? But just be careful, don't make any mistake here. Okay? Okay. So that's change of variable. And when we go to triple integral, and we'll look at this Jacobian again in terms of a change of variable, right? Yeah. What happened to these 3 cancel this one here, right? There's another 1/3 here, yeah. Okay, very good. So I'm going to make use of next time is to deal with the issue I just raised out here. What if you have a not so simple region R like this? Okay, simple region R is very simple, like a rectangle here, like this. You know, all you need is just determine the order of integrals, and then just draw another line across this region, and you have to just draw that line once. That's it, right? You don't need to draw it twice because there's only one case when you draw that. Okay. But there's also this case, maybe you have a not so simple region R like this. So given, for example, if I have a region R like this, okay, then what happens is you might need to, okay, separate this region R into 2 portions, okay? And here's basically the so-called additive rule. If your R is separated into multiple sections, then what you need to do is you need to integrate, okay, separately and then add them together. Okay, that's additive rule. So good? Yeah. So I'll give you an example showing how do we do this additive rule. How do we properly separate this region R into 2 sections or 3 sections? Okay. Yeah. Now there are a couple of other rules, you know, for double integral. Basically, it's an extension from single variable there. Okay. But there's one thing. I think I need to, before I move on to the example, let me give you another property. Okay. So the first property is this: if f of xy is greater than or equal to 0 over this region R, then this double integral will be greater or equal to 0. Okay? Yeah. So it actually makes very simple case. For single variable, if the function f of xy is greater than 0 between a and b, and what will be the integral here? It must be what? Greater than 0, right? Must be greater than 0, because y this basically is the area, right? And when you come to double integral, here's the region R, and your f of xy happen to be on the top of that, okay? To be on the top of that, and it's also greater than 0. Greater than 0 basically on the top of xy plane, right? On top of xy plane. So as we learn the double integral, so what's the one physical meaning for double integral is what? Is the volume between the region R and the top surface, right? If the top surface is greater than 0, what about the volume? It has to be greater than 0, right? Yeah, so that's why it is. Okay. So now let's move on to take a look at this property, additive property here. Okay. So I'm gonna give you a region R, which is kind of special, not as simple as the previous case. It's bounded by 3 straight lines, and the first one is 2x, half x, x plus y equal to 2. Okay, so it's bounded by 3 lines, and this is R here. Okay, star. And we want to integrate any kind of functions, for example, okay, just any kind of function here through this region R, okay, over the region R. So this is the case I've been saying. When you do this, and you've got to be careful, basically, with this region. Because why? Because if you decided to integrate with respect to, let's say, if you decided to integrate with respect to to y first, so you draw, basically, you draw a straight line, okay, across this region R, okay. And it depends on where you draw it. If you draw it here, your minimum is here for the y, and the maximum for the y is here. But if I draw it over here, the minimum is still on this line, bottom line here, same thing. But the maximum is on this line here now, right? It's on this line. So the y max is different. If they're different, then you cannot integrate this through this region R just in one step. So we have to separate this region R separately. So how do we separate them? So the separation depends on basically the number of patterns here. So in this particular case, you can separate like this, right? So you can draw straight lines perpendicular like this. So separate the region R into 2 portions. Okay, yeah. So on each side of this, on each side of the separation, you have a unique y mean and y max. Does that make sense, right? On this side here, let's say this is R1, and this is R2. Okay. Yeah. So let's see what integrals for R1 and R2s are. But before we do that, I think we need to figure out a couple of things that are here, okay, in order to properly put down the limits for the double integral. So let's find what the coordinates are for the point A and point B, the intersection points. So basically 2 intersection points between the lines here. That's pretty easy. So the intersection point for A is between this and this. And for B is between this and this one. Okay? Yeah. So you basically solve the 2 equations and to find the coordinates x and y. And x for the A is going to be 3 over 4 y is 2 over 3. And x for b, 2 over 3, 4 over 3. Okay? Yeah. Sorry. X is, sorry. No, this is 4 over 3. Okay? 4 over 3. Okay, so that's the coordinates for a and b. Okay, so now let's put down these double integrals. R1. Okay. I want to integrate with respect to y first. Okay, so dy dx. Okay, so what's the y limit? What's the x limit when you're integrating over R1, this portion? Okay, this portion. You draw the reading line across R1. First contact is y mean, second contact is y max. So y mean is 1/2 x. And y max is the top one there, 2x. X mean, x max, and you can find them by sweeping this reading line horizontally across region R1. Okay, not not a total R, R1. So basically starting at 0, end up at this location. So x0 to the coordinate, x coordinate of b, which is this, right? This. So 2 over 3. Yeah, is that good? Yeah. So if you know the function, you can calculate this one, right? That's pretty straightforward. Then the next one for R2. So you can do the same thing now. Y mean is the bottom line here, so 1/2 x. And y max is this line here, which is 2 minus x. Okay. X mean x max. You sweep this line from this edge to here, right? From here to here. So x coordinate of b to x coordinate of a, which is 2 over 3 to 4 over 3. Okay, that's it. So I want you to make use the rest of the time. Can you change the order? If I change the order to integrate it with respect to x first, and how would you, what would be the limits, and how would you separate this r? So dx dy. Okay, so let me okay. So first of all, you can integrate in one step. You have to actually do this piecewise integration. In this particular case, you will have to separate at this location. Okay, so separate the region R's like this. This is B and this is A. Okay, so B coordinate X, A coordinates, you already had it. If this is R1, this is R2, so you draw reading lines in the X direction. Okay, how will be the for R1 and for R2. Okay, put down the limits. Okay, so you should be able to finish this by giving this amount of time. I think it is pretty simple now. So for R1, what's the x mean? Okay, what's x mean here? This is R1, okay? This is R1 here. Pi over 2. And here, y minus 2. Okay? And x goes from, sweep these lines across the region, basically from this edge to this edge. So from the y coordinate of A to y coordinate of B, which is okay. For R2, this bottom one here, okay. So y over 2 up to here, 2y. And x goes from 0 to y, 2 over 3. Okay? 2 minus y. Oh yes, yeah, 2 minus y. Good. Thank you. Is that the same? Yeah? Yeah, good. So, just one little trick if you see the kind of region, right? Yeah, just make sure when you draw the line, if you see a different pattern, then that means you have to separate the region. Okay? Any questions? All good? Okay.
Second one should be 2 minus y, the first one should be 3 minus y.
Second one, 2 minus y. Where? Here? This? Yeah.